Now in this problem we have a light source that's placed at the origin, and the illumination at any point x, y in the plane is given by this illumination function, I. If you are at the point 3, 1, in what direction should you walk in order to experience the greatest increase in illumination? What is the rate of change at the instant you begin to walk? And assume the illumination is measured in lumens and distance in feet. Okay, well that means we'll have some good units for this one. So, all right, let's look. We want the greatest increase, right? So that greatest increase is going to happen at the positive gradient, right? So the first thing I want to know is the direction, right? So the greatest increase direction would be the gradient. Okay, well, the gradient on this one's going to be fun because that's going to be a fun one to take the derivative of. Actually, it's not too bad. So because of the derivative of e to the something is e to the something. So let's find that gradient. I think I'm going to put it down here because I don't think I'm going to have room. That would be equal to, oh, here, let me write this up here. Oh, it's not really f, is it? Sorry, that's my fault. This is really I, right? So this is an illumination function. So I should call it capital I here because that's the name of our function. Okay, so that'll be I sub x and I sub y. Okay, so let's find that. The derivative of e to the something is e to the something, so that's pretty easy. This is e to the negative 0.1 times x squared plus y squared times the derivative of the interior with respect to x, which would be negative 0.1 times 2x, right? Because the y squared is going to give you nothing and the negative 0.1 is a constant. So that's negative 0.2x, if you will. And then we're going to do it again for the other one. So e to the negative 0.1 x squared plus y squared times the derivative of the interior, which is negative 0.1 times 2y. All right, so let's think here. We want, we could simplify this, but we don't really have to, right? We really just need it at the particular point that we're looking at, right? So we need at point 3, 1. Okay, so at point 3, 1, what's our gradient? All right, that would be equal to e to the negative 0.1 times, and then we would put 3 squared and 1 squared in here. And then we're going to multiply it by negative 0.2 times 3. And then we'll do it again for the other one. E to the negative 0.1, right? And that'll be, again, 3 squared plus 1 squared. And we'll multiply it by negative 0.2 times 1. Like that. And obviously we are not doing this by hand. Let's not be ridiculous. So I did it in Maple. So let's see here. So I have my greatest increase, right, which is this, and there's my lovely gradient, and then I substituted x equals 3 and y equals 1 into that gradient, and it gave me negative 0.6 e to the negative 0.1 and negative 0.2 e to the negative 0.1. And of course that's not super useful. I'm going to write it, but it's not the best, so I'm going to change it to decimals. So it's negative 0.6 e to the negative 0.1 comma negative 0.2 e to the negative 0.1, which is much better to be written as negative 0.221 comma negative 0.074. Okay, now what would the unit be on that direction? It would be lumens per feet, right? So lumens, because that was what our intensity was, or illumination was measured, per feet, right? Direction we're moving. All right, so this is the direction of maximum increase. And then you could see it on the Maple, I'm sure. The greatest rate of change, right? We found the direction of the greatest rate of change, but the greatest rate of change rate of change, excuse me, itself would be the magnitude of that gradient. So that would be the square root of negative 0.221 squared plus negative 0.074 squared. And of course, I made Maple do it, and it gave it to me as, I think, 0.23, but let me double check. Yep, 0.233. Oh, this is the one that's lumens per foot for my unit. Not A, because A is just the direction, right? So it's giving me feet and feet. So sorry about that. So it's just pointing the way for me to go. But this will be the change in my illumination as I move in that direction, right? Which would be lumens per foot. All right. Next, letter B. In what direction would you begin to walk if you want the illumination to remain constant? Oh, all right. To remain constant means that the gradient must be 0, which is not as hard a problem to do as you might think of. So if your constant illumination, that means that your directional derivative, oh, I just realized I did it again. That's capital I, not capital F, or lowercase f, right? I was our function name. Sorry about that. Okay, so that would have to be equal to 0. Now that only happens when the direction is orthogonal to our gradient. Oh, I did it again. It's I. Now, when would that occur? Well, we learned this trick back in the day. What you do is you take these two and you flip them, and then you switch the sign. So I start by taking the negative 0.074, and I write it right here, negative 0.074, and then I put the 0.221 in back, but I make it positive. So I switched them and made the back one positive, or I switch them and make the first one positive, right? You either switch, so you flip the two numbers and then either make the back one switch sign or make the front one switch sign. But either way, right, there you go. Right, we learned that trick back in chapter, well, the first chapter, the first unit. So I'll just circle these. All right, so we've seen that the gradient can be interpreted as directions of change, right? So the gradient always points in the direction of the biggest positive change. The negative gradient points in the direction of the biggest negative change. The other way to think about the gradient is geometrically, right? The gradient is pointing in the direction of, well, let's put it this way. It's pointing in the direction of biggest change. And so if it has 0 change, that means the direction's orthogonal to the gradient, right? So putting this all together, what do we really mean when we say that the vector is orthogonal to a curve? What we're saying is that it's orthogonal to the level curve, right? Okay, so let's look at this by looking at this example. So 5x squared plus y squared is a paraboloid. It's actually kind of an elliptical paraboloid, so because it's larger in one direction than the other direction because of the 5x squared. There we go. So we have some kind of paraboloid, right, doing this. Okay, so we want to think about the level curves at c equals 1, c equals 5, and c equals 10. And I just did this in Maple, but if you remember how to do it, let me just do one of them. So we would set 5x squared plus y squared equal to 1, for example. And that's an ellipse. You might not be able to recognize it because it's not quite in standard form, but it's an ellipse, right? And then it would go through, let me think. If x was 0, y would be 1. So it'd be going through that and that, negative 1 or 1. And then it's actually like 1 over the square root of 5 for the x if y is 0. So it's doing something like this. So it's in a little ellipse right here. And that's what's happening down here. It doesn't look like an ellipse, but it is. And then you could do it again for, let's see, 5x squared plus y squared equals 5. Divide everything by 5 and we get x squared plus y squared over 5 equals 1. So that's going through 1 for our x coordinates, and then it's the square root of 5, which is about 2.2 or so. So it's going to be going through like that. You can, of course, graph all this on Maple, or you could graph all of it on Desmos to kind of see that I'm telling you true, but I am. I wouldn't lie. Oh, and I thought, so this is another ellipse. Right, so that's an ellipse, that's an ellipse. They're all centered at the origin. So, and then it'd be a higher up ellipse. It'd be, over here on that curve. And I guess I'll just do one more. I might as well, since it asked for it. So at c equals 10, so this was, just in case it wasn't clear, this is c equals 1, this is c equals 5. Just a review of how we did these. This is c equals 10. So you go 5x squared plus y squared equals 10. You divide everything by 10. You'll end up with x squared over 2 plus y squared over 10 equals 1. So that's going to put us through plus or minus the square root of 2, which is about 1.4 or so on the x-axis, and the square root of 10, which is a little bit over 3. So 3 and negative 3. So it's going to be an ellipse like this. So these are the level curves, like that. Okay, so we have our level curves. We sketched the level curves. We're going to compute and sketch the gradient vectors at points 0, 1. So let's find those points. 0, 1, which is right here. 1, 0, which is over here. And 1 square root of 5, which is over 1 up the square root of 5. So it's about there. Okay, so those are the 3 points. And I'm just going to make Maple do this. So I found the gradient. Here, let me show you. I found the gradient. Oh, here's the curve if you want to see it. There's the contour curve. It is elliptical, but I couldn't let it look elliptical because you can see if I do scaling constrained, it looks like that, which it now looks like an ellipse, but it's really tiny. So I didn't want to do that. So I left it wide. But these are the contours. These are the 3 circles we just drew, or the ellipses, sorry, we just drew, concentric ellipses. Okay, so the gradient would be, actually, it's pretty easy to find. The gradient of this is 10x comma 2, 10x, sorry, comma 2y, which is quite simple, right? And it means that it would be easy to find the gradient vectors at these points because we would just stick 0, 1 in. If you put 0, 1 in, you're going to get 0, 2, right? So at the point 0, 1, we're pointing straight up, right? So if I draw that in, it's touching that pink circle. So I just go straight up right there. And that's where I'd end up. All right, then at, let's see, 1, 0, which isn't quite the blue one, but it's close. If I put 1, 0 in, that'll get me 10, comma 0, which is going to go way out past where I can see on this graph. But it's straight out to the right, 10, 0. That's the gradient, right? And then this is 0, 2 for that gradient. And then the last one is the trickiest because if you put 1 in, that's 10, and then you put the square root of 5 in, that's 2 square root of 5. So, nothing exciting there. But it's going like this. It's shooting way out. 10, well past what I can draw because my grid doesn't go that far. So what do we see? What we're seeing is that what it's saying up above, which I was probably jumbling earlier, which is that the gradient is orthogonal to the level curve. So it's always pointing in a direction that's orthogonal to the level curve, right? And the negative gradient, of course, would be pointing the other direction, right? So in other words, if you can see it, we're hitting right angles right here, right? It's a right angle. It's a right angle, right? It's not perfect on the blue one, but you get the gist, right? So the gradient is orthogonal to the level curve. That's what it means when it points in the direction of steepest ascent or steepest descent if you're going the negative gradient. Steepest ascent means it has to be orthogonal to that level curve. It has to be, because level curves are, right, measuring the steepness in their own way of the graph, right? They're contours. So if you want to point in the direction of steepest ascent, you have to be orthogonal to that level curve, wherever that might be. All right, so let me write that down one more time at the bottom. And we could see it happening in this particular problem as we were doing it. Those gradients were perpendicular to their respective curves. Exactly, right? Because gradients are always perpendicular to the level curves due to their nature, due to the fact that they are pointing in the direction of steepest increase. That means automatically they must be perpendicular to the level curves, or orthogonal to the contour curves, if you want to think of it that way.